thing we'll talk about in more detail later is memory models. Basically what happens is a compiler and a CPU are both free to reorder reads and writes. So the rules that govern basically how the compiler is allowed to reorder reads and writes is called the compiler's memory model. For instance, there's a Java virtual machine memory model that controls how the Java virtual machine is allowed to do this reordering. Similarly, CPUs can reorder based on whatever the rules are of their memory model. So sometimes you have to really be aware of this, especially really if you've got two CPUs that are trying to access data, let's say that one has written. So for instance, if CPU 1 writes A and then writes B, CPU 2 may expect that if it reads B, that A has already been updated. And that's not necessarily the case. So it may be A and B are written, CPU 2 reads A and B, gets an old value of A and a new value of B, because either the writes were reordered or the reads were reordered. One good thing is the x86 memory model says that exchange. Okay, so that means that any values that are written before the exchange appear by the time the exchange happens. This is what's called a barrier. We'll talk about that later. Okay. The nice thing is if you're using locks, that means that once you have acquired the lock, once you've done the exchange, that anything that has been written before that is available to be seen on other processors. When you are dealing with sort of, let's say, vanilla use of locks, that's all you really need to know. But if you're trying to do exotic coding, like let's say you're trying to do lock-free coding where you're not using locks, then you need to be aware of every detail of the memory model and make sure that what you're doing fits within that memory model. While we're waiting for a lock, right? So if you've got a CPU waiting for a lock on a spin lock, it can't be doing anything else, right? It's sitting there inside acquiring, spinning, right? Basically running at full speed, just sitting, waiting, doing exchanges, waiting to get it. So if you are waiting for some critical section that may be long, that can be wasteful. So what we can do is, during a lock, give up the CPU and switch to another process. So the idea is you would only use a spin lock. So this is called a blocking lock, by the way. So the idea is you use a spin lock for short critical sections, where short means they don't take very much time. So I don't care how many instructions there are. And then use a blocking lock. Commonly what will happen with a blocking lock is that blocking locks have higher overhead, but the ability to yield the CPU. Okay? In some cases, you can have locks, for instance, that start out as a spin lock and kind of see if they can quickly acquire it, and if not, then we'll go ahead and turn into a blocking lock. So let's look at some suggestions in conclusion for using locks. So one, don't share if you don't have to. If you're not sharing, you don't need locks. A second suggestion would be to start with coarse-grained locking. That is, lock at, let's say, a module level or something like that until you have actually measured to determine what is preventing parallelism, right? That you've got, let's say, some very large section of code that other CPUs are waiting on. So instead, if you can reduce the amount of code that is controlled by the lock, you can increase the parallelism. So the idea then is measure, and only once you've identified the opportunities for better parallelism. And just as a reminder, this might be, let's say, for a file system, instead of having a lock around the entire file system, have, let's say, locks on directories and on files, for example. And then the last suggestion is when you're using locks, it is easy to have bugs that are hard to reproduce. So use automated tools. Automated tools like race detectors to find locking bugs. And don't forget also, if you've got, for example, a routine where you expect a lock to be held when you enter the routine, go ahead and throw an assertion to that effect at the beginning of the routine. Assertions are a fine way to both document what it is you are expecting and also to actually have a runtime check that will throw an error if not. Because if the assertion does fire, then you have some error in your code that you need to fix.